Okay, so this section is about finding confidence intervals for small samples. So when the population standard deviation is not known or the sample size is less than 30, what we're going to use is a t-distribution. So the critical values for the t-distribution are going to be different from the z-score that we've been using previously. So let's talk about the properties first. All right, so some basic properties. The mean, median, and mode of your t-distribution are going to be equal to 0. The t-distribution should be bell-shaped and symmetric about the mean. The total area under the curve is still going to be 1 or 100%. You're going to notice that the tails, the ending part of the t-distribution, are going to be thicker than the standard normal distribution. And the standard deviation of the t-distribution is going to vary based on the sample size, but it is going to be greater than 1. Something else that you will see when we're dealing with the t-distribution is something called the degrees of freedom. So what essentially is happening when we have degrees of freedom, it's kind of like that, that game that people play around the holidays, where you're exchanging gifts and then somebody has the right to steal the gift or something. And essentially one person is gonna end up not having a choice in the matter. And so that's where degrees of freedom comes into play, is because once all of the samples have been taken, there's only going to be one left, so the last person is not going to have a choice. So to calculate your degrees of freedom, you're going to take however many is in your sample and you're going to subtract 1 away. So you'll notice with our t-distribution, the bigger the sample, the closer it's going to get to our standard normal curve. Okay, so after 30, after sample sizes of 30, pretty much the t-distribution is going to map to the standard normal curve. Okay, so let's go ahead and do an example. So for this first example, they want us to find the critical value when the sample size is 15. Okay, so the first thing that we're going to do is we're going to calculate our degrees of freedom. And to do that, we're going to do 15 subtract 1, which is going to give us 14. Okay. So then what we're going to do is we're going to look at the chart to figure out what our critical value is. All right, so if I'm looking here, our degrees of freedom was 14, and we're doing 95% confident. So here's 95% confident, and I'm going to go down to 14, and that's going to give me 2.145. Sorry, the chart's a little bit hard to read. I'm also going to be posting online a better chart that gives you a little bit more degrees of freedom options than just up to 30 like the textbook does. Even though typically once we get higher than 30, we just use our standard normal curve. Okay, so the critical value is 2.145. Okay, so we can also do this in the calculator. Okay, so I'm going to write down the steps first. So same problem that we just did. So the steps are stat, then test, and then t-interval, and X bar is going to be 0. S is going to equal the square root of n. I'm going to use the right value and ignore the negative. Okay, so let's go ahead and do this. So stat, and then test, and then t interval, and x bar is going to be 0. Oops, 0, square root of 15, and 15. And my confidence level is 95%, so 0.95. Enter, and it's thinking. All right, so you're going to use the right value. So it's 2, can you see that? 2.145, you're going to ignore the negative. Okay, so 2.145. All right. Okay, so let's go ahead and do another example. Okay, so for this example, we want to find the critical value at 90% confidence when the sample size is 22. Okay, so n is 22. Okay. So my degree of freedom is going to be 21. And so I like to use the chart rather than the calculator. I don't know, something about it, just nice. So 21 and 90% confident. Okay, so 21 and 90% confident, 1.721. So remember, you're going over to the correct confidence level, and then you're going to go down until you match up with your degrees of freedom. Okay. All right. So much like we were dealing with our large samples, we can find the confidence interval for our mean using our t-distribution. Okay, so the formula looks really similar, except this time instead of my z critical value, I'm using my t. Okay. All right, so let's just run through this in words, and then we'll do a full example. Okay. So first, you need to make sure that you do not know your population standard deviation. If you do, then you can just use your normal distribution, provided that it is normally distributed. Okay. Your sample needs to be random, and the population still does need to be normally distributed, or your n has to be greater than 30. And then you're going to identify your key pieces. What is the sample number? What is the sample mean? What is the sample standard deviation? You may have to find this if they give you a set of data. Then, very key, you need to identify your degrees of freedom, because that's going to help you with your chart. Find your margin of error. So your margin of error formula, very similar to what we did in the last video, except this time we're using the t critical value instead of the z. And then you're going to calculate your endpoints, subtracting and adding the error to the sample mean, just like before. All right, so let's kick this off with an example. Okay, so we have 16 coffee shops, and we are measuring the temperature of the coffee sold at each of them. All right, so first I'm going to write down the fact that my n is 16. which means my degrees of freedom is 1 less than that. It's 15. The sample mean temperature is 162.0 degrees Fahrenheit. So X bar is 162.0. The sample standard deviation is 10 degrees Fahrenheit. Okay. And do I know anything else? 95% confidence interval for the mean temperature. Assume the temperatures are normally distributed. Okay, fantastic. All right, so the first thing that I'm going to do is I'm going to find my critical value using my degrees of freedom as 15 and my confidence level of 95%. So if I look at my chart, oops, just hit the camera. Okay, so if I look at my chart, it was what, 15 and 95%. So 95% and 15 is 2.131. Okay. Should probably just like leave that open rather than keep closing it. Okay, let me focus this because I hit it. Okay, that's crooked. All right. So what was I? 2.131. All right, fantastic. Okay, so my formula for my margin of error is my t critical value times s divided by the square root of n. So it looks very similar to what we were doing in section 6.1. So my t critical value is 2.131 times 10 divided by the square root of 16. It's going to give me about 5.3275. All right, so then all we have to do is we need to add and subtract that to our mean. So my mean was 162, and I'm going to subtract 5.3275. And I'm going to add, and I'm going to get 156.7 degrees Fahrenheit and 167.3 degrees Fahrenheit. Okay, so what we can say, our summarizing sentence is, we are 95% confident that the mean temperature of coffee sold is between 156.7 degrees Fahrenheit and 167.3 degrees Fahrenheit. Yeah, ooh, that's a little hard to read. I'll try to write a little bit bigger on the next one. Okay. All right, next example. Focus this a little bit better. All right, if you want to pause the video and try this one, you totally can. All right, so you randomly select 20 cars of the same model that were sold at a car dealership and determine the number of days each car sat on the dealership lot before it was sold. The sample mean is 9.75 days. Okay, so N is 20. My degrees of freedom is 19. Mean is 9.75. Sample standard deviation is 2.39. Construct a 99% confidence interval for the population mean as for the number of days the car model sits on the dealership lot. Assume the days on the lot are normally distributed. Okay. So first, we need to find our confidence critical value. So our degrees of freedom are 19. And we're looking at 99, so all the way at the end of the chart, we're going to get 2.861. Okay, so just like before, let's go ahead and find our error. So to find our error, we're going to take our t critical value multiplied by our standard deviation divided by the square root of our sample number. So 2.861 times 2.39 divided by the square root of 20. And I'm going to get about 1.53 days. Okay, so what that is telling me, r minus e. So 9.75 plus 1.53 and 9.75 minus 1.53. Ooh, I totally did that backwards. Oop. So this should be minus and this should be plus. Okay. All right, so then I will get 8.22 on this side and 11.28. These are days. So we could say with 99% confidence, the population mean for the number of days a car is on the lot is between 8.22 and 11.28 days. Okay. So now you're probably thinking, well, how can I tell the difference between when I need to use the Z and when I need to use the T? And I don't even know. Okay. So there's a really fantastic chart on page 322. So I'm going to grab that so we can look at it. Okay. So if you're looking at this chart, the first thing that you need to ask yourself is your sample bigger than 30? And if it is, you're going to use your normal distribution with your Z. Then if it's not, you're going to ask yourself if it's normally distributed or not. If it's not normally distributed, you can't use either the Z or the T. If it is, then you need to ask yourself, is the population standard deviation known? And if it is, you can actually use your normal distribution with the Z. And if it's not, that's when we're going to use the T distribution. Okay. So let's run through a few examples where we're just trying to figure out if we're going to use the Z or the T. So it says you randomly select 25 newly constructed houses. The sample mean is 181,000. The population, ooh, ding, 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 standard deviation is 28,000. Assuming the construction costs are normally distributed, should we use the normal distribution, the T distribution, or neither to construct a 95% confidence interval? So the key thing here is, even though my N is 25, it's less than 30. What we do know is that it's normally distributed, and we know the population standard deviation. So since we know the population standard deviation, we're going to use the normal distribution. All right, let's look at another one. Okay, you randomly select 18 adult male athletes. Okay, so N in this case is 18, which is less than 30. The sample mean is 64 beats per minute. The sample standard deviation is 2.5 beats per minute. Assuming the heart rates are normally distributed, should you use the T, the normal, or neither to construct this? Okay, so the question is, do we know sigma? And the answer is no, it is unknown. So since sigma is unknown, but this is normally distributed, we can use our T distribution. Okay. All right, one more. In a random sample of 19 patients at the hospital, so N is 19, the mean waiting time before seeing an emergency medical professional is 23 minutes, with a standard deviation of 11 minutes. Assuming the waiting times are not normally distributed, should you use the normal distribution, the T distribution, or neither? All right, so key thing here is it is not normally distributed, which means, guess what? We can't do it. None.